right, so let's look at this, just kind of look at these summaries here. So in calculus, when you calculate, so this is called this walk. So here the int simply represents, it just says that it's called the internal energy of the system. Internal energy. But we can calculate, so you can calculate, so in this example here, this ds is the length so it's the small, so in calculus, it's just like the small length vector. So suppose that you have, this is positive, this is negative, so you have an electric field. So an electric field is going to act in this direction. It means that if I put a test charge here, the test charge is going to move like that because there is a force acting on this test charge. And so force times distance gives me energy, all right? So basically what I can do is that I can go ahead and do my integrals there. And so we define this potential energy change using this equation. So if you, I think I showed you this equation last time. So the electric potential is just, you can think about this as the potential energy divided by the charge. Okay. So that's an important equation. Now some of this is going to sound confusing, but once we start applying this to solve problems, you're going to notice that we're just going to focus just on a few equations, all right? But the thing is that just think about an electric field pushing a particle, so push. So the electric field is pushing this. This is my test charge right there. Test charge. So place a test charge at rest, the electric field is going to push it in that direction like this. Okay. So basically, when you so the change in electric potential between 2 points is given by this equation here. So it's the integral of the electric field vector times the length vector. So ds is the length. So in terms of units, the delta V is measured in volt, and 1 volt is 1 joule per coulomb. And then, so the electric field is measured in Newton per coulombs, but sometimes we can also represent an electric field as volt. All right, so with this, I'll just move on here. Now, what this shows you is that, so we can measure electric, so UE, I can measure this in joules. And sometimes it's also convenient to measure this in electron volt. So EV is called the electron. So the electron volt is a very small unit for energy. So for example, you can see that 1 electron volt is equals to 1.602 times 10 to the negative 19 joules. So that's the conversion factor between an electron volt and the joules. Now, what is the electron volt? The electron volt simply means that if the potential difference between 2 points is equals to 1.0 volt, and if my test charge is the charge of an electron, which is 1.60, 2 times 10 to the negative 19. So I'm saying that if an electron was to move between point A and point B, so you have an electron that moves between point A and point B, and if the potential difference between point A and point B was 1.0 volt, then the electron is going to gain an energy that is given by charge of electron times VAB. So if you just multiply 1.0 times 1.60 times 10 to the negative 19, you get this energy right here. So now this is mostly used. So if you look at this picture, this is a picture of something that is called the dental. So this is the dental X-ray. So when we talk about X-rays, we don't use joules, but we use electron volt. So as an example, just to give you an idea, so typically, so dental X-rays typically use maybe about, sometimes like 10 to about 20, so this is called the KeV, so kilo electron volt. So dental X-rays use very low energy X-rays, it's about 10 to 20 kilo electron volt. If you try to compare that with X-rays that are used for therapy, so for example, for the treatment of cancer, so this is about 10 mega. So you can see that the type of X-rays that you use for treatment of cancer is like very, very high energy. It's about 1,000 times much more energetic. That's why when you do a dental X-ray, you don't worry a lot about the dangers, right? But if you're going to go somewhere where there is a source that produces X-rays for therapy, then you got to be very careful because those energies are very, very large. Then there's also X-rays that we use for imaging. So for example, if you want to see a broken bone, so for imaging, it's about 100 to 500 kilo electron volt. So typically, the type of X-rays that we use for imaging is typically in those ranges. All right, so I'll leave this quizzes for you guys to take a look at. Now, let's start to look at some examples. So the first example is when you have a uniform electric field. And I want to calculate the potential difference, which, if I use this equation here, so this is my key equation here, it's just this integral. Now, looking at this picture here, so in this example, you can see that the electric field you can write it as, let's say, some magnitude, the negative j, because it's pointing down. And then you can say that your ds vector is also dy, and the negative j hat. So if you take the dot product of these two vectors, you just get e dy. And then you integrate that from, so you want to integrate that from point A to point B. So you can say, for example, at point A here, ya is equals to 0, and yb is just equals to my distance d. So if you do this calculation here, you get this value for the. So without looking at all these integrals here, you can see that when the electric field is not changing, the potential difference is just the magnitude of the electric field times the distance. And most of the times, we just forget about this negative sign here and just work with the absolute values. All right, so let's look at, so what if the electric field was acting such that the displacement is not at 90 degrees with respect to the electric field? Then you're going to write this equation as negative Q, magnitude of E, magnitude of displacement times the cosine of the, because this is called the dot product. So remember that when you calculate the dot product of two vectors, it's equal to the magnitude of vector 1 times the magnitude of vector 2 times the cosine of the angle between the two vectors. Okay. Now let's take a look at this one example here. Example number 22.4. So this is called the electric field between two parallel plates of opposite charge. Now, what you see in this example, suppose that you have a, so in this example here, I have a 12 volt body. Now I'm going to take the positive and connect it to the positive of one plate and the negative. So when I do this here, I create, so I make this to become positive here, and that to become negative. And then there's going to be an electric field line that goes from the positive to the negative like that. Now, it tells me what the potential difference. So for example, in this case here, you can say that the potential at point A is 12.0, and the potential at point B, you can just call this 0. So that the change in the potential is going to be 0 minus 12. Then it also tells us that the distance between the two plates is 0.3 centimeters. And so what we want to calculate is that we want to calculate the magnitude of the electric field between the plates. And so we're going to assume that the electric field is constant. It's a uniform electric field, it's not changing. So if I scroll down to my next slide, you're going to see that when I calculate, so this equation comes from, remember we said that VAB is equal to VB. If I keep the magnitude, this is just equals to the electric field times distance. And so solving for electric field, you can say electric field is equals to, let's say, to the magnitude here. This magnitude of VB. So if you go ahead and plug in the values, 12.0 volts for the change in the potential between point A and point B divided by distance, you get this value. The electric field here, so you can also write this as 4.0 times 10 to the power 3. So Newton per Coulomb is the same as volt per meter. Now, how can you prove that this is the case? So how do we show that a volt per meter? So I want to prove that volt per meter is the same as Newton per Coulomb. If I want to do that, how do you show that 1 volt per meter is equal to 1 Newton per Coulomb?
1 volt is, well, volt is joules per coulomb, and then joules is force times distance. So all of that together derives.
That's correct. So you just go ahead, so we know volt is joule per coulomb, right? And joule per coulomb is Newton meter per coulomb. So if you substitute this here, then you should be able to prove that 1 volt per meter is the same as 1 Newton per coulomb.